Okay, let's get started. Now that we've covered some very established memory technology, DRAM, and then talked about in-memory computation, and then looked forward to emerging memory technologies that are not that established, but that are hopefully going to be happening. So if you're lucky, we'll see an emerging memory technology next year in the DIMM slot. That'd be great, actually. Let's talk about a technology that was emerging like 20, 30 years ago, and that has emerged and that has been extremely successful, and in my opinion that has revolutionized our lives all across. And that's flash memory. And I'm going to give you a short background on flash memory operation. How many of you know how flash memory operates? Oh, okay, that's good. So if I ask you questions, you'll be able to answer? Somewhat. Okay, good. At the very low level? Yeah. Okay, good. How many of you don't know how flash memory operates? Don't be scared. Okay, okay, that's good. This will be fun, I think. I mean, like any memory technology, there's no magic in this also. And this is charge-based memory. So basically, I'll give you the high level first. So if you look at NAND flash memory, it's actually very much block-based. Internally, it'll look like DRAM at some point, but the memory array is divided into blocks, and you actually, whenever you need to do a write, you don't need to, basically if you want to write something, you initially erase an entire block. So the erases are done on a block granularity, and that's to minimize the cost of erases. But you can write at the page granularity, and you can read at the page granularity once you erase the block. Erasing means setting the voltage level to the minimum voltage level possible in the entire block itself. So a block can be pretty large. Basically, it can have 256 pages, for example, each block, and each page is about 8 to 16 kilobytes, for example, in flash memory. So remember, erase at the block level, such that everything becomes 0, and then you can write at the program at the page level. That's called programming or writing. You write at the page level. And then you can, of course, read at the page granularity as well. Okay, so if you want to read a page, this is what needs to happen. Basically, you need to apply, if you want to read a page in this block, page 0, you need to apply a read reference voltage, which we will talk about what that is, to that particular page. And you need to apply a pass-through voltage to everything else. And this is because of the way flash memory operates, which we will go into. And this is going to be interesting, but this is a little bit different from how we do in DRAM, right? In DRAM, what we did was, if you want to read or activate a page or a row, you applied you applied a high voltage to that word line, and you didn't touch any of the word lines, any other word line. Here, it's different because things are connected in a NAND string. It's called a string, flash string. To optimize for very high capacity, everything is connected in a string. All of these transistors and different pages in a single bit line is in a string, and you need to ensure that whatever you're reading from the string passes through such that you can sense it in the sense amplifiers. And that's how it operates. It's a different technology. That's how it works. Okay, so let's go into a little bit more detail. So this is a block, and these are the pages, as you can see. This now looks like a subarray, as you can see, but it operates a little bit differently. So if you look internally, it looks much like DRAM, except now what you have is these are floating gate transistors. Basically, these are the flash cells that can store data, and whether you have charge or not, encodes data that's stored over here. And this can be very dense, because if you can look at this, it's just one transistor, right? That's it. There's no capacitor. It's just a transistor. And how small you can make that transistor limits your scalability in the end. And this can become very dense. And the rest is similar, basically. You have sense amplifiers at the bottom, you have word lines over here, and you have bit lines over here. The difference is the transistors are on the bit line. Right. If you look at DRAM, if you remember DRAM, the transistors, nothing is on the bit line. You just connect the capacitor through an access transistor to the bit line. Here, the transistors are naturally connected to the bit line, so whenever you're reading one particular cell over here, you need to ensure that these don't interfere with that reading. That's why you need to apply high pass-through voltage to those cells, and you need to apply a read voltage over here. So we'll go through that. So that's a row, very much similar to DRAM, and that's a column, again, very much similar to DRAM, but I already told you the difference. So a flash cell looks like this. It's called a floating gate transistor, at least in planar flash, planar meaning two-dimensional. We'll talk about three-dimensional a little bit also. But in two-dimensional flash, this is the dominant transistor type that has been very successful. It was invented, I think, in, I don't know, late 1970s or so, maybe even earlier. But basically, you have this floating gate that traps charge and stores charge, and you have the drain and source and the gate, as you can see over here. And you store the threshold value, threshold voltage of this cell that you program it to determines the value that you store over here. So you can, for example, program this. This is usually programmed with what is called incremental step pulse programming. If you really are interested, you can read some of the papers that I'm going to reference. But incrementally, you increase the voltage over step by step. Basically, you have these small voltage steps, and you incrementally pump voltage into it and increase the voltage to a level that you want it to be at, such that that level is encoded as whatever you want the cell to reflect in terms of data, right? And we will see that also. So let's assume that the threshold voltage is 2.5 volts, right? And when you program threshold voltage, after you program it, you apply some other reference voltage, and the cell reacts in some way, depending on what the voltage that it's programmed to is over here. So it can actually store the voltage forever. It's non-volatile, at least forever, meaning theoretically forever, of course, right? But in practice, you have a lot of other effects. Okay, so this is threshold voltage. Basically, this is on the x-axis, you have this normalized threshold voltage, and we'll see a lot of these graphs over here. Right now, this is a flash cell with very few electrons programmed to it, low voltage. You can encode that as a 1. And this is a flash cell with lots of electrons programmed in the floating gate. Basically, this is high voltage, and you can program, you can encode as a 0, right? You can assign any kind of logical encoding to these two different states. And then you have a boundary between these that tells you what is the difference between a 0 or 1. Basically, a reference boundary over here, and we will see that also. So basically, let's take a look at two cells. One is programmed at 2 volts at threshold voltage, and the other has a threshold voltage of 3 volts. And let's assume your boundary is 2.5 volts over here. What you do is, if you want to distinguish between what the cell is containing right now, you apply this read reference voltage that you know is 2.5 volts, because that's how you program the cells. You apply this read reference voltage to it. Now the cell turns on, meaning basically passes the value if the read reference voltage is greater than the threshold voltage. In this case, it's like that. You get a 1 over here. Now the cell is inhibited if the read reference voltage that's applied to the gate is lower than the threshold voltage. It doesn't turn on. As a result, it inhibits what's coming from the bit line. Remember, there's a string of transistors over here. As a result, you get a 0 over here. So that's how you distinguish between these two cells. You apply a read reference voltage that's known, and one of them reacts with a 1, and the other one reacts with a 0, which makes sense. Right? Okay, that's the flash read. Okay, I think I've already given this. Okay, so pass-through, so this is how you can distinguish the value. But if you don't want to read a row, what you do is kind of obvious. Pass-through means you apply a very high voltage that's higher than any value that any cell is programmed to, and then you make sure that this cell passes through what's coming. The cell turns on, and it passes through what's coming over here. That's the idea over here. That's how you ensure that some rows pass through the values that are coming through the bit lines. You apply a very high voltage. That's called the pass-through voltage. Make sense? Okay. So let's take a look at the read from a cell array with an example. Let's assume that we programmed the cell array to these values somehow earlier using incremental step pulse programming. But there are other programming methods people have developed, but ISPP tends to be the most common one today. Let's assume that we want to read page 2 over here. If you want to read the contents of page 2, we want to apply the read reference voltage to the word line of this page, and we want to apply the pass-through voltage to all of the other word lines over here. Essentially, this is what we do. And when we do that, these two transistors are inhibited because their threshold voltages are higher than the read reference voltage, so they don't pass through what they have. so you get a 0 at the end, whereas here they pass through what they have, so you get a 1. And these don't interfere because they're always turned off, if you will, right? Because the pass-through voltage is, at least the voltage that you apply to the gate is always higher than the values that you see on these pages that you're not reading. As a result, in the sense amplifiers, you get 0, 0, 1, 1, which is really what you want by reading that page. Of course, there's a sense amplification process over here also, which we're not going to talk about. Okay, there's an aside that I wanted to put over here. I wish I had made these figures a bit larger, but the difference between NAND and NOR, you may actually see NAND and NOR flash memory. NAND flash memory is much more common today because of its very high density. NOR flash memory is not that common today, although its latencies are relatively low, its density is not very high, and it may not be as scalable. But we're not going to go into the NOR memory as much. At some point in the lifetime of overall history of flash memory, there was a big debate which one is going to be more successful, which one is going to be better. And it turns out that NAND flash memory won because of its density advantage. And as you can see, the density advantages, the bit line looks like this over here. Basically, this is the bit string that you have. And all of these transistors are connected to the bit line in a NAND fashion, which is what we actually looked at over here, which was NAND. Whereas here, it's like a NOR fashion, basically. You can see that the bit line is like this, and the bit line turns on if any of these transistors actually turn on. But as you can see, this actually is not very dense. So you have a lot of these additional lines, as opposed to having a single string where you can really nicely put things on. Here, you don't have that single string. But the word reading is relatively fast over here because you don't go through the entire string. So the capacitance is much lower over here. So we're not going to talk a lot about NOR memory because it's not as high capacity, but it's interesting in the sense that it's a different type of flash memory. It uses the same type of transistor. They're organized a little bit differently in a NOR manner as opposed to a NAND manner across the entire bit line. Okay, makes sense? But this is also fast. The advantage is this is fast. Faster than NAND. Okay, let's go back to the threshold voltage. Basically, this is what we said. You want to program the cells. You have a read reference voltage that delineates a 1 from a 0. And if you want to program a cell to the 1, you program it to this level. If you want to program it to the 0, you program it to this level. Now, naturally, there's a lot of variation in the programming. Programming cannot be extremely precise. So whenever you do the programming, your threshold voltage will not be exact. It turns out there's variation. So usually what happens is you have a distribution across the flash cells that you programmed. If you program them to 1, some of them have threshold voltages that are over here, some of them have threshold voltages that are over here. If you program them to 0, some of them have threshold voltages that are over here, they're really close to this 1, and some of them have threshold voltages that are around here. And this happens because of program variation, which is a factor of process variation, how precise your programming equipment is, and many, many other factors. The factors in terms of cell as well. And the papers that I'm going to reference actually look a lot into those issues. But yeah, this exists and you have to deal with it. I mean, this is also true for DRAM cells actually, if you remember, DRAM cells store different amounts of charge, except we never showed them in this way. We show them in this way because we actually are a little bit more precise in terms of how much voltage we inject. And we can actually read the reference voltages that we program cells into in flash memory. We have a lot more control because of the machinery there. Okay, so basically you will see these threshold voltage distributions. This is called the threshold voltage distribution. It's a normalized threshold voltage, and it's probability density function, as you can see. So this is more highly probable. This is more highly probable, and this is the threshold voltage distribution for state 1 and for state 0. Okay, and a lot of problems will appear because these threshold voltage distributions are not that nice as I depict over here. They actually overlap with each other, especially with a lot of factors that happen. And that's exactly why it's hard to make these memories work. But we're going to develop a lot of techniques to make them work. So okay, basically you select your read reference voltage such that it's actually hopefully nice. It basically delineates this distribution from this other distribution such that you get no errors. Right? If these distributions were overlapping, you would get errors. And we will see that. Okay, so this is called single level cell, meaning a single cell denotes a single bit. But if you want to go to multi-level cell, as we've discussed with PCM, it's relatively similar. You chop up the threshold voltage range into 4 in this case. And now you have different states. You have an erase state. It's usually called an erase state because this state is actually not programmed, right? You erase the block, and if you don't want to change the value from that, you don't touch it. You don't program that cell. Actually, it usually has negative voltage because you don't touch it. You raise it to 0, and over time it drifts to negative. As a result, we're not going to show it. We're not going to be able to even measure it in a lot of distributions in real life. Okay, but this is, you need to program this P1 state to 1, 0, and P2. In this case, I encode as 0, 0 for the reasons that we've discussed in the past. But again, you can put any encoding here. And this P3 set. So now you've seen that actually the threshold voltage distributions became much narrower. And maybe you don't have enough control to actually make these read reference voltages as nice as I showed you. Okay, so the upside is you get higher capacity, clearly, with the same threshold voltage range. You didn't change anything in the structure, but you chopped up the threshold voltage range into 4. Higher capacity, you doubled the capacity. But now you need to use 3 different threshold voltages to identify a cell's value. And the other downside is your reliability may have reduced because your distribution may not be as nice. The distribution may actually span partly these threshold voltages. So as I said, the erased state is actually erased. You don't program it. So we're not going to see a lot of the erased state in the measurements that we will see because it usually has negative voltage. Okay, so we're going to look at things like this. There are 3 states to encode 4 values. There's also the erased state, but we're not going to measure it. So these 3 states look like this. But there are issues. Like one issue we're going to talk about is over time, charge gets lost. That's the fundamental issue with charge memory. So when charge gets lost, what happens is these threshold voltage distributions shift like this. So they've just shifted, as you can see, from here. Maybe it was nice to begin with, but over time, some of the cells lose charge and they shift. Now what happens is, if you were reading using this read reference voltage, these cells were correctly read in the past, but now they're going to be incorrectly read as 0, 0. You were thinking they were 0, 1, and they were correct, but your read reference voltage is wrong. I don't want to say wrong now. The cells actually shifted to a value that's below the read reference voltage. As a result, you get bit errors when you're reading this cell. And that's true for this side also. All of these cells that are in this distribution that have shifted to the left of this threshold voltage, this read reference voltage, are actually going to be read incorrectly. So that's a problem. So what you can do is basically, if you have a fixed read reference voltage, that's what happens. But if you're able to adapt your read reference voltage to what's happening in the device, you can say, oh, okay, some of these cells actually store data for, let's say, 5 days. And because they've stored data for 5 days, my read reference voltage should not be this, but it should really be this. If you can find that out, then that sounds good, because this is the place where you really minimize the raw bit errors, right? You really want to be crossing the point. You really want to be at the point where the distributions cross if you want to minimize the raw bit errors. And that's exactly one of the mechanisms that existing flash controllers use. This is called the optimal read reference voltage. They basically try to find the optimal read reference voltage to minimize these raw bit errors, because these raw bit errors are a lot. I'll show you real distributions from very small devices in a little bit, and you'll see that they actually overlap very heavily. Okay, makes sense, right? So how do these real controllers do this? Basically, they have a mechanism called read retry. They are able to actually change the read reference voltage and check the value, check the number of errors. So what is usually done, one algorithm is, for example, they read with read reference voltage, and then they get the values. The values go through error correction. If the error correction doesn't pass, they change the read reference voltage and read again. That's one algorithm. Of course, existing controllers are even more sophisticated today. They don't even try, because that's not a good algorithm in the sense that increases your read latency, right? Especially if you want to do it many times over and over. Because these steps, the voltage steps, are relatively small. If you want to get to a point where you don't have errors, hopefully, if it's possible, you want to find the read reference voltage that gives you a read that's correctable by ECC. Right? But that may take time. That may take like 10 steps, meaning that 10 times you do the read of the flash. That doesn't sound good, right? It's already a slow device. If you're doing the read 10 times to get the right value, that's 10x more latency. So what existing controllers will do is use techniques that I'm going to describe a little bit. They actually try to predict what the threshold voltage would be over time. And they don't try to, they try to minimize these retries as I described them. They try to predict, okay, maybe 5 days later the threshold voltage will be this, so they try to adapt the read reference voltage. So there are a lot of models that these controllers actually build, and they're building them online, during online operation today, to basically characterize the distribution and basically characterize, have a model inside that basically predicts, okay, the distribution will be like this, given that the data has stayed here for n days, given that neighboring page have been programmed, maybe with these values, and as a result, I'm going to pick a read reference voltage that's here. And we're going to talk about some of those models, but there's a lot of very, very interesting research that has gone into it to minimize these raw bit errors, because these raw bit errors are actually a lot. Okay, so how do you actually program these cells? Actually, if you have a 2-bit multi-level cell NAND flash memory, you normally program it using like two-shot programming, what we call it right now, and that increases your latency. Basically, what you do is you normally program the LSB, or least significant bit first. Essentially, so this is the first step, or two-step programming. Sometimes actually there are two types of programming mechanisms. One is called one-shot programming, and the other is two-step programming. A lot of flash memories use this two-step programming because it's more precise right now, because you program one bit first and then the other bit next. But actually, if you have a very large cell, sometimes it's okay to use one-shot programming. And actually, with 2D NAND, cells have become very small, the planar NAND. As a result, people move to this two-step programming a lot, but this of course increases your latency. But when actually people were able to figure out how to do 3D NAND, they increase the cell size, so they're back to one-shot programming, meaning that they can control the cell more precisely. As a result, they can actually program 2 bits at the same time. But that's going to change again, I think, as things scale. They're going to go back to two-step programming like this. But basically, what is two-step programming? You program the LSB, least significant bit first. So in this case, least significant bit is, I guess, 1 or 0. So basically, erase state, you don't do anything. If your least significant bit is 0, you go to this temporary state. Temporary state, you don't know. It could be any of these, right? If the least significant bit is 1, you don't do anything. If least significant bit is 0, you go to this temporary state. And then you program the most significant bit. Well, I guess if your most significant bit is 1, you move from the erase state to this P1 state by adding some more voltage. And if your most significant bit is 0, you go from this temp state to this P2 state by adding some more voltage. And then if most significant bit is 1, in this case, I encoded things a little bit differently. The most significant bit is on the right, least significant bit is on the left. So this is a big endian, as you can see, which I don't like, but that's how it happened to be. But basically, you program the second bit next over here. As a result, it's two-step, and this takes time. This takes time, and then this takes time. But it's more precise because you're doing it in 2 steps. Okay. Okay, so if you look at multi-level cell architecture, it actually looks like this. I'm not going to go through this in detail, but basically, you have these LSB even page sets. You can see them over here. And then you actually have LSB odd page sets. These are least significant bit. You have this separation between odd and even pages. And then you have most significant bits over here, even and odd. But you can read the papers for more detail. It's nothing different from what I just described. But the difference over here is, as you can see, whenever you're programming, the interesting thing over here is whenever you're programming, you apply very high voltage. So this is about 20 volts in this example. That's a lot. And you also need to inhibit everybody else. That actually is about 10 volts. So programming these things actually take a long time. That's why the write latencies are long and the energy is very high also. So ideally you want to program minimally. Okay, do I have anything over here? Okay, the other thing I have over here is nothing. Okay, you can see the MSB and LSB over here also. That's fine. But basically, if you see these figures, that you should think about corresponding these to these states over here. One thing that I will talk about over here is the order in which you program things matter. So you usually As I said, this is LSB odd page sets, MSB even page sets. So the order in which you program things matter, because whenever you program, you cause interference to the adjacent word lines because of these voltages that you apply. And the way people usually do programming of pages after they erase a block, the way the pages are programmed is they want to minimize that interference. And there are algorithms that are developed to minimize that interference. I'll point you to a paper that talks about that. It's interesting, but it's basically you want to minimize the interference such that you don't destroy the values in the pages that are next to you. That's the idea. So that's called write disturb essentially, or program interference. Okay. So controllers need to be aware of that also. So let's talk about planar versus 3D NAND flash memory. For a long time, planar memory was very, very successful. It was hitting the scaling limits, just like DRAM is hitting the scaling limits right now maybe, because it was two-dimensional. Basically, people scaled the cell by reducing the cell size, reducing the distance between the cells, and as a result, they were able to get high capacity. And what's the difference? This is two-dimensional, as you can see. Three-dimensional NAND flash memory, you stack these cells, and I'm going to show you an example of this. Basically, you can increase the number of layers. So this turned out to have scaling issues. Scaling actually hurt reliability a lot, and a lot of methods have been developed to improve the reliability, to make this work, basically. And we're going to talk about a lot of those methods. 3D NAND flash memory, recently, this is actually a revolution within the flash memory. People invented how you could stack the floating gate transistors in a single bit line vertically. And now, because they were able to do that, they actually broke the boundaries of this 2D planar thing, if you will. And they were able to actually stack things vertically. Now they have another level of freedom, right? You could actually put things in a vertical way. And as a result, they were able to increase the size of the cell. Here, the size of the cell was 1x nanometers or 1y nanometers, 10 to 15 nanometers. Here, now the size of the cell is 30 to 50 nanometers. So actually, they increase the size of the cell, which is good for reliability. And they were able to get high capacity by actually stacking many, many layers. So there are existing chips that are out there that have 96 or so layers in 3D. The issue is, of course, this is not well studied, and we're going to talk about some works that are studying it. So this is actually a very open and very interesting area in terms of reliability as well as other optimizations in 3D NAND flash memory. Okay, so this is an example of 3D NAND. Basically, it's kind of obvious, but you have these bit lines that are vertical, and the layers are actually horizontal, and layers are actually word lines over here. And we're going to look at the, inside you have these transistors over here. And most of these are charge trap transistors. So this is the flash cell right now. And this is a charge trap transistor. There's multiple technology. You could actually have floating gates over there also, but charge trap tends to be easier to manufacture right now, although in future we will see what happens. Basically, the way this works is relatively similar to what I just described at the abstract level. But internally, the way it's implemented looks like this. You have a substrate over here, you have a charge trap, and you trap the charge inside this charge trap transistor, and you have the control gate, and the gate oxide, and the tunnel oxide. Okay, I don't want to go into the detail. You can read the paper again. But you can see this nice picture. This is basically, it's nothing different from any memory that we examined, except it's three-dimensional, right? This is the three-dimensional bit line. It goes across, and this is the word line that cuts the bit line. And your blocks look like this now. Your blocks are essentially three-dimensional, if you will. And this is the other block, and this is the other block, right? And you have the sense amplifiers at the bottom. Make sense? Okay, add another layer, of course, that's a sense amplifier layer. Okay, so if you're interested, actually, there's a lot more background, and we recently written a survey, an invited survey paper that talks about flash memory, as well as many, many other things that are employed in flash memory. And that was published in Proceedings of the IEEE. I would recommend that you take a look at it. This is really, we put like more than a year of effort into writing this paper, and more than 8 years of research that we have done, and also we have observed based on what other people have done. So this is really the state-of-the-art summary. I'm very proud of it. And it's about 40 pages or so, I think. But of course, after we wrote it, we know that it was obsolete at the moment, and then we wrote the more up-to-date version, which is also obsolete at the moment, but at least it's the most up-to-date version that's out there right now. So this was actually the more recent version that's on archive.org. It's also in this book that's called Inside Solid State Drives. There is actually a lot of other stuff related to solid state drives. If you're interested in that, you can look at the book as well. But it's not my book, other stuff. This chapter is ours. So this is actually more up-to-date because it talks about 3D NAND a little bit more, but it doesn't really have the most state-of-the-art things in 3D NAND. So the more up-to-date version is hopefully coming in 2019 or maybe 20, depending on how much time I have. Okay. But this actually has a very accessible view of how flash memory operates. It talks about other stuff like garbage collection, which we're not really going to talk as much about today. Okay, maybe I'll talk about it. But maybe I'll talk about garbage collection a little bit. So garbage collection is, you have these pages in flash. So if you want to write to a location, change the value of a page, it's not easy, right? As we've seen. What do you do? Because let's assume that you have read this page and that you modified the contents of that page. Now you need to reprogram it. Reprogramming it is not easy because you cannot just write to that page, because when you want to actually reprogram, you only can increase the voltages. If you want to decrease the voltage, you need to erase it. But there is no mechanism to erase a single page. Erases are done only at the block granularity. And this is a trade-off that was made for cost reasons, because erases are actually extremely expensive. As a result, flash manufacturers said, we're going to do erase at the block level. And as you saw, blocks are 256 pages, right? And you do erase at the block level, but you want to modify only that page. Now you have a problem. You read the page. What do you do? Well, what you do is actually have blocks that are writable at that moment. So you have a set of blocks. Some of them are erased. Some of them are currently being written. And some of them are valid, meaning you already have valid data inside them. And the flash translation layer needs to keep track of them. If you want to read a page and write to it, what you do is you read the page, you modify the value, and write it to some other block that you're currently writing to. Which means that you actually remap the page, right? You remap the page from this location to this location. So flash translation layer, one of the big jobs of the flash translation layer is to keep track of what block exists where, because it does a lot of these remapping. You have a logical block address that gets remapped to physical locations, because whenever you modify, you actually cannot directly modify, you need to remap it. That's the idea. Now, okay, you remap this page from this location, from this block, to this other block. Actually, let's give an example over here, if we can. So we have block 0, let's say block 1, block 2. Let's say this is completely erased somehow. And this is the block that you're writing to. So open for writing, I'll call it. Meaning some of them are erased and some of them are being written to, because you've just erased it and you're directing your writes over here. And this is a block that is basically, let's assume that it has, it's not erased, it's not open for writing, it's populated. So these are 3 different types of blocks. This block you cannot write to, because writing requires erasing. This block you can write to some pages. And this block, yes, you can write to, but you're waiting such that you can utilize this part first, because this is open for writing also. So this is open for writing. This will be open for writing in the future after you're done populating this. So basically, flash controllers need to maintain a logical block address to a physical block address mapping table. Your logical block address, let's say, I don't know, is 0. Initially, it's mapped to here. But when you want to write to it, you read the block with the reading mechanism that we discussed. You modify 1 bit. Doesn't matter how many bits you modify. You modified 1 bit. You need to write the entire, this page. So this is actually at the page level, right? Because you're doing operations reads and writes at the page level. You basically write to this page 0 and block 0. which means that you read the data, you modify one bit, and you write the page to the next available physical page in the open block that's open for writing, which means that you need to change this pointer in the flash translation layer from here to here. But which also means that the flash translation layer needs to be aware of everything. Now what happened to this? That's obsolete. That's tail value. So flash translation actually keeps another table that says these are my invalid pages. I mean, this could be organized in different ways, of course. And this could be one linked list. So one of the invalid pages is block 0, page 0. I've written it somewhere else. So that's invalid. I cannot do much to it. I cannot erase it. There's some value over there. So it's basically invalid. It's waste. Okay, so let's assume that you've done some of these to some of the other pages over here. And remember, this is 256 pages, let's say. And let's assume that you've written 200 of them somewhere else, because you're writing to those blocks. You've changed their mappings. Now you have only 56 valid pages here, right? Meaning that you're really wasting most of your block right now. So actually this is, so what should the controller do right now? So sometimes, this depends on the algorithm of the controller, but sometimes what the controller say is, heck, I don't want to waste a lot of this, so I'm going to move those 66 pages to a block that I erased. In the background, I'm erasing stuff because I'm smart. Make sense? So that's one way of doing it. So this is kind of an example of garbage collection, because these invalid pages are actually garbage. Meaning you don't care about the data in them, they're just wasting space. So you want to maximize your space utilization inside the drive. As a result, you need to collect that garbage once in a while. And this is an example of garbage collection. So how do you set the threshold? Maybe you wait until there are no valid pages here, right? Then that's really garbage. The entire thing is garbage, then you can erase it. But you can be proactive also. You can say, oh, I'm wasting most of my space in this block, so I'm going to declare this as mostly garbage, and I'm going to move the useful stuff to some other block, and then I'm going to erase it such that somebody else can use it. So controllers are doing this in the background all the time to ensure that they have enough space over here. And this is happening because the read and write granularity is at the page level, and erase granularity, well, I shouldn't say write granularity. Okay, read granularity is at the page level, and the erase and program granularity is at the block level. And the block level is huge. And that is there because of technology constraints. So of course, to be able to do that, what the controllers usually have is, usually the space in flash drives are over-provisioned, meaning that they actually have more blocks than advertised to the customer, so that they can actually handle this sort of moves more efficiently. Of course, over-provisioning is not good in general. Ideally, you don't want any over-provisioning because that costs, right? You would like to minimize the over-provisioning, but over-provisioning happens naturally because you want to handle these cases. Okay? Then the key question, there's actually really interesting questions over here. Like now you have actually another level of freedom. You have these different pages, and maybe you know their characteristics. What should you collocate in a block? Ideally, you want to be smart about this also. If things are going to be written a lot, maybe you collocate them in a single block. If things are not going to be written a lot, maybe you want to collocate them in a single block also. But you don't want to mix them. There are some pages that are very hot in terms of writes, and there are some pages that are not very hot in terms of writes. If you mix them, you run into the situation that I just discussed over here. Some of them will be garbage, some of them will not be garbage, right? But if all of the pages in your block are very hot in terms of writes, you keep writing to them, that's good. Put them all together such that that block quickly becomes garbage and quickly becomes non-garbage afterwards. And if you have a collection of pages that you know are not going to be written a lot, they're read-only, maybe you keep them in a single block. That way, that block is not going to be touched much for a long time. That's one trade-off. So that sounds good. Of course, it's not that simple because of other issues with the device, right? The device has another issue which is called wear out. So if you keep writing to only a single block, that may be good for this garbage collection purposes, but that's actually terrible for wear out purposes because you keep wearing out the same block all the time, right? So you want to balance that. You need to actually do the wear leveling across the blocks or across the pages actually to ensure that you want to distribute, you want to have because, okay, what is this is the endurance problem that we discussed. A block, for example, you can only do 3,000 writes to a given block. 3,000 program and erases or page. Now, if some of the pages have over here 3,000, if some of them have 0 over here, that may not be good, right? Because you're not utilizing your entire drive. Some of them becomes unusable quickly, and some others become unusable, right? Maybe it's better to level this wear or wear out across the blocks somehow, such that you level the number of writes across the blocks. The question is, how do you do that while also trying to minimize the garbage that you have? That's why the design of the control is actually a very complex design, because these things actually go against each other. And also there are other issues. Like if you actually say, okay, I'm going to collocate these blocks that are read very heavily in the same block, there are other error mechanisms that you need to watch out for, because there are read disturb mechanisms that we're going to talk about. If you're reading a lot, a particular page, you're disturbing other pages. So your reliability for that block may go down, and you may need to have more ECC or mechanisms for that. So what data to place where becomes actually very, very interesting, given all of these different constraints. And there are many, many different constraints, and we will see some more of them soon. Okay, so I said I don't want to talk about garbage collection, but you know what garbage collection is right now. Okay, any questions while I do this? Okay, so let's talk more about flash memory reliability, because in addition to all of these latency and performance issues, reliability is very, very important. And I'm going to focus more on reliability right now, because that's something that's really required to make the memory work. And I think I said at some point that this memory doesn't work off the bat. You really need a controller that's intelligent to make it work. By the way, I talk about erases, but these erases take a huge amount of time. So they take 10 to 100 times longer than a read. So scheduling is another issue that we're not going to talk about, for example. How do you schedule these requests? Because you have read requests, you have erase requests, you have refresh requests, as we will talk about. How do you schedule all of these requests to flash memory becomes interesting. Ideally, you would like these erases to happen in the background. That's what these controllers try to do. They try to make sure that while things are idle, if they happen to be idle, they erase as many blocks as possible, such that those are available for writing later on, but that's not always possible, of course. They try to minimize interference. So these are some of the issues that you should keep in mind, but we're not going to talk about all of them at the same time. But let's talk about errors, because this is actually a fascinating area. And you know this picture before. Flash memory is charge-based memory, so it's prone to a lot of errors because of charge. So I'll cover a bunch of hopefully really interesting works. This is an executive summary of it. Basically, NAND flash memory reliability and endurance is a key challenge for satisfying future storage systems requirements. I'm going to talk about that a little bit. And then I'll talk about some of the works that we have done and that are being employed in the field and that are based on two goals. One is we want to actually build reliable error models for NAND flash memory via experimental characterization, similar to what we've done for DRAM, for example. But we can be much more precise over here because we have the luxury of measuring the voltage of every single cell. It's not possible to do that in DRAM. And we'd like to develop efficient techniques to improve reliability and endurance. So basically, this is going to be a flash summary of recent results that talk about experimental error and threshold voltage characterization, retention of error management, and a bunch of other stuff. We'll see that. Okay, and actually more, but it doesn't fit over here. So let me give you some more high level. Basically, this is a picture from 2011 from Hynix, actually. And this shows what flash memory has gone through in terms of scaling. So it's actually, it's like scaled perfectly almost until somewhere around here. You can read the numbers over here, but this is MLC flash memory. You can get 64 gigabits, and basically you get very good scaling. That's what I should say over here. And as a result, it's actually widened its range of applications everywhere, because you could put a lot of bits into a very small space, much more dense than DRAM, less dense than hard disks, but hard disks are actually very cumbersome, right? They're huge, and they're totally different technology. As a result, they don't have the good characteristics of flash memory. Okay, the key question at that time was actually how do we scale into the future? And this actually is still a question, but it's delayed a little bit more because of 3D NAND. So this is one example over here. This is again from Flash Memory Summit in 2012. If you look over here, this is years, and this is the program erase cycles. How many program erase cycles can a page endure before it gets dead, before you cannot read from it or write to it? And if you look over here, this is single level cell. It looks good, 100,000 or so. This is multi-level cell. It's about 3,000. And this is triple level cell. You store 3 bits per cell. And that's very low. It's getting close to 100 over here. And actually, some more aggressive ones I know are 100. So the provided program erase cycles are a few thousand, let's say. Pick this one. But if you look into storage requirements, the program erase cycles that are really required, these are standards actually, is by STech, that's a storage technology corporation that a lot of companies get together and they say, okay, we want to be able to write the full capacity of the drive 10 times per day for 5 years. If you want to do that, you really need more than 50,000 programming erase cycles with a decent capacity. So there's a mismatch over here. The device provides a few thousand, you really want more than 50,000 if this is your application level requirement. So how do we bridge the gap? So one way of bridging the gap is of course over provisioning, right? The device advertised itself to be 1 terabytes. Internally it's 4 terabytes. Now it can actually manage itself, but that's not a good solution, right? That's an expensive solution. Remember, expensive solutions are possible, but that's not the goal. An engineer is someone who does for a dime what any fool can do for $1. Okay, so basically, how do we bridge the gap? We're going to talk about bridging the gap. So one way of bridging the gap is potentially using ECC, but I'll actually show that it's not a very good idea, perhaps. So this is another view of this. This is again from 2011, but the trends are actually very clear at that time. So this is single level cell, this is 5x nanometer multi-level cell, 3x nanometer multi-level cell, 2x nanometer multi-level cell. You see that endurance is decreasing. And it's 3-bit, so endurance is about 1,000 cycles. So endurance decreases with scaling as well as multi-level cell as expected. So if you want to, you can actually add error correction capability. And if you want to guarantee storage class reliability, which is uncorruptible bit error rate is less than 10 to the minus 15, you actually need to add a lot of ECC. So the bit error rate is a little bit different from endurance. Bit error rate is how many bits are erroneous. 10 to the minus 15 is something that you would like to achieve. If you would like to achieve that, you actually want a lot of ECC. So this is error correction capability is 4 bits per 1 kilobytes of data. Here you need 24 bits per 1 kilobytes of data. In Flash, error correction is done in large blocks. We're not going to go into that in detail. Some of the papers talk about that. But basically, you need more bits, more redundant bits, which actually takes away from your space also, right? So this graph is very telling because you're actually getting less endurance, but you're putting more ECC inside the chip to get the high error rate. So how do you actually, basically ECC is, the ECC that you require is increasing exponentially to reach less endurance, but keep your error rate at least at 10 to the minus 15. So this doesn't sound good. So this was a clear scaling problem, and that's one of the reasons why we wanted to look into this from the research perspective. And when we first started looking into this, actually, we were behind industry, meaning that industry knew a lot more than us. Now I think industry knows in some areas more than us, but we could actually affect the industry because we are able to invent, and they take some of the ideas. So sometimes it's good to actually go into research even though you know that you're behind, because you can leap forward much faster. Okay, so basically the problem is the NAND flash memory is increasingly noisy. you can think of a single bit, even a single cell, as a channel. You write into the cell, and something happens while you're writing and while the cell is sitting there, and then you read something out of that channel, and what you read may not correspond to what you write. So you can think of this as a communication channel, right? You have a communication channel over here that happens to be the cell. You transmit on this end, and you read on this end, and things happen in between, and you can model what those things happen. But a lot of things happen actually in between. So let's talk about that. It's a noisy communication channel. That's why I think actually communications people look a lot into memories as well. I think this is a very good approach to examine memories as communication channels. Okay, so basically, if you look at flash, you have some noisiness, and you get some row bit error rate that's usually high, and you want to do something to it such that your uncorrectable bit error rate is less than some requirement. So you clearly need to apply some error correction mechanisms somehow. You need to be intelligent about them. And maybe you need to apply something else such that you reduce the row bit error rate that you get over here. I'm going to call that signal processing, because a lot of these things will look like signals. Okay, basically you want to minimize the raw bit error rate that we get out of these devices, and we want to actually do better error correction or more intelligent error correction such that we satisfy the requirements. So how do you actually do this? First, you need to understand. As I said earlier, for DRAM, you want to be able to understand. You want to build the reliable error models for NAND flash memory. And you want to design efficient reliability mechanisms based on the models. Let's take a look at what happens to a flash cell over its lifetime. So first of all, you write into it. What we wanted to do was to experiment to characterize and model dominant errors. So what are those dominant errors? And this is the first paper that I'm going to describe that was published in 2012. So you write to the cell. What does that mean? You need to erase a block at some point. You need to program the page. And you get errors in both. Whenever you're erasing a block, erase is not a complete clean erase, because you get errors. There is no erase that's error-free in flash. That's the beautiful technology, unfortunately. And then you program a page, you get errors. You actually inject errors to others. So we're going to talk about some of the errors that we characterized. And then while the cell is sitting there, you're not even touching the cell anymore. You programmed it, you erased the block, you programmed the page, fine. Now some neighbor page gets programmed, and whatever you have in the cell gets disturbed because of cell-to-cell interference. And you need to understand that. And there are ways of understanding it and ways of building mechanisms to overcome it. And we're going to talk about that. Okay, that happens. Even if nothing else is happening around the cell, neighbor page, by the way, is any page around in the same block. So you actually have 256 minus 1 pages that can affect you while you're sitting there. And even if nothing affects you, you're subject to retention errors, because the data over there is sitting and you may not read it for a really long time, and charge leaks. As a result, you have a retention problem, and you need to deal with that somehow also. So we're going to look at some of these errors, and as I said, a lot of these are, actually all of these are described in that paper that I mentioned that I'm proud of. Okay, so let's talk about the goals again. We want to understand these error mechanisms and develop reliable models that are predictive for the flash memory errors, and develop efficient error management techniques to mitigate errors and improve flash reliability and endurance. As I said, you want to improve reliability, improve endurance, and also improve the row bit error rate. So basically, we're going to do a lot of experimental analyses of real MLC NAND flash memory that will drive the understanding in the models. And hopefully understanding models and the creativity associated with architecture will drive the new techniques. And here's another example from that paper that I mentioned. These are the different types of errors. Program erase cycling, that's wear out. Program cell-to-cell interference, data retention, read disturb. This is in planar flash. There's also some more in 3D flash. And these are some mitigation mechanisms that we're going to talk about. Maybe not all of them, but I already talked about hot data management, for example. That's employed in flash drives, but maybe it's not the best way. It's not employed in the best ways. Okay, and I'll point you to those papers. So let's talk about the experimental characterization methodology a little bit. So we're going to characterize these errors, meaning that you actually really need to have an infrastructure to be able to do that. And this was the infrastructure that we had. This is an initial incarnation of the infrastructure. It's relatively similar to the DRAM infrastructure, and we have a NAND flash controller, and we have a flash translation layer, in this case, inside the FPGA. And let's talk about the first error types that we're going to examine. There are 4 different error types. 3 of them are caused by common flash operations, and we're going to initially characterize these: read errors, erase errors, and program interference errors. And one of them is caused by flash cell losing charge over time, and that's the retention errors. And of course, whether an error happens depends on the required retention time, when you're going to read the data. For example, if you're going to store your pictures in a USB drive and you're going to read them 6 years later, that's a lot of retention time. You may want to read them earlier, because those drives are actually some of the worst flash memories, and they are subject to all of those errors, and they don't have many of the error mitigation mechanisms inside there. So retention depends on retention time, of course, when you're going to read these things. And this is especially problematic in MLC flash because threshold voltage window to determine the stored value is smaller, as we've discussed. So this is what we're going to do. Basically, this is what happens to a page over here. You start, you program and erase, one cycle, you program, erase again, program, erase again, program, erase again, and after some point you cannot program or erase or read. And that's when the page dies. So this is, you erase a block and you program a page, and you program the entire thing over time, maybe, and then after the cell is programmed, it's subject to retention, and we're going to test different things. We're going to test a small amount of retention, a large amount of retention, how long, what is the distance between the time you programmed and the time you're going to read the page. So you get erase errors over here, you'll get program errors over here, you'll get different retention errors over here, read errors over here, and different sort of retention errors over here. So what we've done initially was, at that time, this is 2011, actually 2010 or so, we characterized error rates of 3x and 2y nanometer MLC NAND flash. I always forget, is 3x 30 to 35 or 35 to 39?
30 to 30.
Okay, that's better, yeah. So x is the lower one, y is the higher one. So y is this 2y is 25 to 29, let's say nanometers. They don't want to tell the exact technology level, that's why we keep it this way. Technology node. Okay, basically we're going to characterize that, and we're going to quantify the raw bit error rate at a given program erase cycle. Raw bit error rate means the error rate that you get before error correction, before you employ error correction. That's a fraction of erroneous bits. And we're going to quantify the error correction capability and area and power consumption of various error correction code implementations. I'm not sure if I have slides for that, but the papers cover that. And as I said, as you increase the error correction capability, your area and performance overheads increase, and the benefits that you get will not be very high. So basically, we are going to identify how much raw bit error rate each code can tolerate, and how many program erase cycles each code can sustain as a result of this. So let's talk about these first two a little bit, and I'm going to give you some main characterization results. So there's certainly a measurement methodology. You can read this, but basically erase errors, you count the number of cells that fail to be erased to the 1-1 state clearly after you do an erase operation. Program interference, you compare the data immediately after page programming and the data after the whole block is programmed. Read errors, you continuously read a given block and compare data between consecutive read sequences. And retention is interesting because there are different retention times. You compare the data read after an amount of time to data written. And there are short-term retention errors. We look at them under room temperature, but long-term retention errors, for example, then you need to emulate. Meaning, if you want to look at the effects of retention time, that's 3 years. Clearly, we're not going to wait for 3 years, because that's going to be a very long experiment. So what we do is we actually use heating to emulate the effect of long-term retention. And people have actually shown that Arrhenius equation, which basically predicts the error rate based on the temperature, holds over here. But I'd be happy to talk about that. The papers actually have that detail. Okay, so let me give you some characterization results. This is the initial results. You can read the paper for more detail, but basically, this is what happens. This is the curve. This is the program erase cycles, how many cycles that a block has been programmed and erased. And this is the raw bit error rate that you get. And this shows which errors are dominant. And it turns out, that's the first thing is raw bit error rate increases exponentially with program erase cycles. Raw bit error rates, you can see this is a logarithmic scale. And it's increasing exponentially with the programming erase cycles. That's not good, first of all, which means that as flash memory becomes written a lot more, your robot error rate increases. And this is the fundamental problem. If you want to maintain some endurance level, you want to actually ensure that your robot error rate stays lower, which means that you need to add ECC or do something about it. And the second interesting thing is retention errors are dominant. For example, if you want to read data after 1 year, that's the 1 year retention errors over here. That's this curve over here, the red one. Not the red one, the thing below the red one, the green one. You see that more than 99% of the errors that you have at a PE cycle of 10 to the 5 is mostly retention errors. The rest of the errors are, yes, there, but they're not very high. This is program interference, this is read errors, this is erase errors. So erase errors are actually relatively low, as you can see, but they're increasing also over time. But retention errors are the dominant. And if you actually want to read the data after 3 years, they're actually even higher. So actually all of these are retention errors. That's the first observation, which was actually very interesting at that time. Now it's not that interesting. But retention errors also increase with retention time requirement, as I said. So what is the retention error mechanism in flash? It's charge loss. It's nothing fancy. You basically lose electrons from the floating gate, and that causes retention errors. And it turns out cells with more programmed electrons suffer more from retention errors. And threshold voltage that you have is more likely to shift by one window than multiple. And that's hopefully obvious also. Basically what you have is you have stress-induced leakage current that you have ongoing constantly. And this is what happens. Your threshold voltage distributions shift to the left. And once they shift to the left, your read reference voltage doesn't work well, as you can see over here. And it's very similar to DRAM. There's value dependency in these errors. This basically looks at the value dependency of the retention errors. And it turns out cells with more programmed electrons tend to suffer more from these retention errors. So going from 0, 0 to 0, 1 is the highest fraction of the errors, as you can see. And those are the states that have more electrons, as you can see over here. And 0, 1 to 1, 0 is also pretty high, as you can see over here. And the remaining is, but clearly there is a value dependency because of the voltage level of the cells that you program them into. This is also similar to DRAM, right? If you remember. So there's a lot more data, and this is the paper. This is actually the first academic paper that has real data from real flash chips. A lot of the things that we've written over here was actually known to industry, and we knew that, but it was not known publicly outside. And we were lucky to have some industry collaborators who actually designed the state-of-the-art SSD controllers at the time, and they're still designing that, and they have enabled us to actually get to a stage where we were able to do these studies. This was actually fun. It's really interesting that not a lot of real data was present at that time. The industry had written some papers, but they really didn't provide a lot of information about real data. So I think this points to the importance of having real data in the field. And this has actually enabled a lot of other people to do research in the area. Okay, so let me finish the retention errors, then we'll take a break. So, okay, we figured out that retention errors are the most dominant errors. They actually limit the programming erase cycle. So if I actually go back over here, there's an interesting thing over here. So you can set your ECC capability to satisfy some retention raw bit error rate. So you can do the calculations. You can say my ECC is going to be 40 bits per 1 kilobyte block, and those 40 bits, assuming some distribution of errors, can satisfy a retention error rate of 10 to the minus 3. Right. Now if you do that, and if you have this information, you can say, oh, my ECC is capable of handling 10 to the minus 3, and I can draw this line over here, and I say, oh, I expect my flash drive to die after some number of PE cycles, assuming retention errors were the only errors in the system. Right. If course, to be able to really do the study, you need to compound all of the errors, and you need to have a usage model. So if your ECC is 10 to the minus 3, and if 3-year retention errors are the only errors in the system, you can actually go up to 10 to the 4 programming erase cycles. So this is actually one way of setting how much ECC that you want if you actually have this information. Now you can actually develop ECC, error correction mechanisms, that satisfy a certain raw bit error rate. That's one way of using this data, for example. Well, it's very valuable. If you don't have this data, how do you actually set your error correction bits, error correction codes to achieve a certain programming erase cycles? That's not so easy. It's actually art at that point. But now it's becoming more science. Okay. Okay, we talked about this. Now we have retention errors. How do you cope with them? Well, you can add ECC, but we already know that that's not a good solution to retention errors, right? Well, we have another solution, which is refresh. And we're going to do that. This is non-volatile memory, flash. And many people don't know that it's actually not refreshed, but now everything is refreshed in flash, especially in data center SSDs where things are powered on. Okay, the basic idea is we want to refresh periodically. You change the period based on the programming erase cycle wear out. You refresh more often at higher programming erase cycles. Because initially, there are not much retention errors. Retention errors are not a problem at lower. So if you go back to this figure is very telling actually. If your programming erase cycles are low, your raw bit error rate is not that high. Basically, if your flash drive is not very used, that's okay. Even if your retention time is long, no problem, because your raw bit error rate is not high. But if you keep using your flash drive and if you have written a lot to it, meaning your programming erase cycle count is high, then raw bit error rate becomes a problem. Meaning that if you haven't written to your flash drive, maybe you don't refresh it much often, but you start refreshing it more often over here, you start refreshing it more often over here, you start refreshing it more often over here, maybe you start refreshing it every hour over here, right? So that's the idea. The idea is to adapt the refresh to the programming erase cycle count in your flash drive at higher P cycles. Of course, now how do you do the refresh? I'm going to talk about this. Refresh is interesting because retention errors, you lose charge. Refresh is really not writing some random data, right? It's really, you need to increase the voltages. It turns out you can actually do this in place, meaning that whenever you do programming of a flash page, you can increase the voltage, but you cannot reduce the voltage. If you can increase the voltage, in refresh you need to increase the voltage, which means that you can actually program that particular page you need to refresh in place without moving it somewhere else. So that's one of the ideas that's employed in existing drives actually right now, but that may not always be a good thing. Sometimes you may want to remap this particular page or all of the pages in this block to some other place. And we'll see the trade-off between them, because if you actually do in-place programming, increase the voltages, you're causing program errors to adjacent pages. But you're not causing programming erase cycle problems because you're not remapping. If you're remapping, you're not causing program errors to these pages over here, but you're causing some other issues. So there's a trade-off between these. And this paper discusses that trade-off. It introduces how to do refresh in Flash. So let me go over the key observations. So we've already observed this. We want to limit the retention errors limit flash lifetime as they increase over time, and retention errors can be corrected by refreshing each flash page periodically, obviously. So the key idea over here is to periodically refresh each flash page, correct its errors using weak error correcting codes, and either remap it to a new physical page or reprogram it in place. That's the idea. So it's called correct and refresh. It's not just refresh, because you need to read the page first, correct the errors using some error correcting codes that you have, and then either remap it to a new physical page or reprogram it in place, meaning you increase the voltage levels. Of course, you do this before the page accumulates more errors than correctable by the error correction codes that you have. So you need to do it early enough. So the optimization that we have is you can adapt the refresh rate to the endured programming erase cycles. You start without refreshing. For a year, for example, you don't refresh your flash drive, not a year. For the programming erase cycle count, some number of programming erase cycles passes. After that, you start refreshing. After some threshold programming erase cycles, you start refreshing more. So there are two key questions over here. One is how to refresh. So how to refresh in DRAM is not a question, but in Flash is a question. And when to refresh. When to refresh is shared with DRAM. So how to refresh, you can remap a page to another one, as we've discussed over here. You can reprogram a page in place. That's what this paper introduces. Or you could have a hybrid of remap and reprogram, depending on what you want, how you want to optimize your error rate. And when to refresh, basically you can have either a fixed period like DRAM, not so good, or you can adapt the period to retention error severity. And we're going to do that. So basically, the proposal is to have a hybrid of remap and reprogram and adapt the period to retention error severity. So let's talk about this in-place refresh. This is also called in-place reprogramming. You can actually do this if you know your data values whenever you actually want to write a different data pattern to the page, as long as your different data pattern is always increasing the voltages. Right? But that's not going to be easy to determine, right? But refresh, you know that you need to increase the voltages. So this is the floating gauge voltage distributions for each stored value. We know about this. Retention errors shift these voltages to the left. And if you do incremental step pulse programming in place on the same page, you basically shift the voltage to the right, and that fixes the retention errors. That's the idea over here. The big pro is there's no remapping that's needed, no additional erase operations. The con is you increase the occurrence of program errors because while you're programming, you're affecting what's happening around you. And there's a trade-off. If you're introducing too many programming errors, this is not good. At that point, you need to switch to remapping-based refresh. And this paper discusses how to and when to switch to remapping-based refresh. Okay, that's the idea. So let's take a look at the benefit, actually. The benefit is actually very interesting. It's very telling. So this is a different amount of BCH codes. BCH codes are actually very famous codes, error-correcting codes. I cannot spell the last names of the last two people, but I know the first one is Bose. It's named after 3 people who developed these codes. But basically, you can read about them, and they've been used extremely heavily in flash memory. Now flash memory is actually transitioning into something called LDPC codes, low density parity check codes, but we can talk about that, and the paper that I mentioned talks about that a lot. But this is different error correction capabilities you have, and these are different mechanisms. Baseline is no refresh, and this is the normalized lifetime. One is basically 512-bit BCH codes. At that time it was reasonable. And basically you have one over here that you cannot see, but that blue bar over there is 1. And this is what happens if you use remapping-based refresh. This is what happens if you use hybrid refresh. And this is what happens if you actually have adaptive hybrid refresh. Adaptive meaning adapt to the lifetime that you have. So as you see, base no refresh, if you go from 512 byte codes to 32K byte codes, yes, you gain some lifetime, about 4x, but it's not a lot. If you do adaptive rate refresh, you actually increase the lifetime by about 46x, which is a lot, which is good. And lifetime of FCR is much higher than lifetime of stronger ECC. So if you strengthen your ECC, that's not a good way of dealing with retention time errors, because retention time errors actually increase exponentially with lifetime. That's the problem that you're facing. And if you want to, you need to really increase your error correcting capability exponentially, and that's not sustainable. Even if it buys you something, and that something is relatively low, that low increase in lifetime comes at very high complexity. And the paper actually analyzed the complexity of ECC, but I'm not going to go over this right now. So it's very clear to everybody right now that ECC is not a good way of handling these errors. As I mentioned earlier, if you know your error mechanism really well, design a correction mechanism that adapts to your, that's a good fit for your error mechanism. Retention errors are not random errors. Retention errors happen because things shift, and you can actually easily fix them by refreshing. And okay, this is another thing over here. Basically, there's always a question, of course, what is the energy overhead of refresh? This is the energy overhead if you do it every year. This is the energy overhead if you do it every 3 months, every 3 weeks, every 3 days, and every day. So even if you do it every day, which is close to the end of the lifetime probably of flash, it's not that bad. And if you do hybrid refresh, it's even better. Remapping-based refresh causes a lot more energy overhead because you're remapping pages. And you can imagine how much energy overhead flash is causing in your system because it's always remapping pages, but you don't want refresh to add more to it. So initially, you're not going to actually refresh a lot. As a result, initial overheads are not large, but as your flash becomes older, written more, older meaning written more, then you need to refresh more. And this is a paper that goes into more detail. And this is, as far as I know, all of the industry-grade SSD controllers implement something very similar to this. They actually refresh flash memory. USBs, good luck. So there's a huge variety in terms of flash memory also, and its quality as well as the controller's quality. The industry grade, like data center grade SSDs that are dedicated and that are expensive do a lot. And of course, one of the downsides that the paper discusses, if you want to be able to do this, you need to be powered on, right? Your SSD needs to be powered on to be able to refresh clearly. Okay. And this is an extended version of the paper, actually, which appeared at the Intel Technology Journal, which usually is restricted to Intel folks. But they were nice enough to invite us to write a paper at the Intel Technology Journal. So I'm happy about that. Okay, so we're going to talk about more errors, but I think it's probably a good time to take a break right now. Let's take a short break for 8 minutes, and then I'll spend 20 more minutes discussing flash memory errors. So let's be back at 1440. Okay, let's continue, since we don't have a lot of time. And this is such an exciting topic that we could spend days and days on it. But we're not going to do that, because there are so many such topics, right? Okay, so we've covered the retention errors right now, but as I said, there are many, many other errors. So let me give you an overview of some of these errors. If you're really interested, this paper actually does a lot of justice to these errors. Let's talk about the threshold voltage analysis and program interference. So basically, one of the other key questions that we have is, that we had next, is how does this threshold voltage distribution of different program states change over a flash lifetime? And can we model it accurately and predict the threshold voltage changes before they happen? And can we build mechanisms that can correct for these threshold voltage changes, thereby reducing read error rates? Perhaps one other way of handling retention errors is by changing the read reference voltage. That's not the best option, but that could be handled that way. Okay, so this is real data from 2 Y nanometer chips using the read retry mechanism. So we are able to characterize the threshold voltage of different states, as you can see over here, at different programming array cycle counts across the device. And the device does vary leveling, so 1K cycle count meaning it's leveled across many flash blocks and flash pages. So this is the threshold voltage distribution that we had seen before in cartoon, but this is real measurements from real devices. So as you can see, there's the probability density function. It's normalized. We don't give out the voltage values because they're proprietary. But you don't see the erase state because its voltage is somewhere over here, and it's not measurable actually. But if you look over here, it looks like a nice distribution. It's actually, we modeled as a Gaussian distribution with additive white noise. Keep that in mind. We're going to change that later on. It looks Gaussian, but that was a good model, but actually over time things change and we'll see different models. So this is the threshold voltage distribution at 1K cycles, 3K cycles, 8K programming array cycles, 15K. So as you can see, as the number of programming array cycles increases, the threshold voltage distribution's shape changes. It shifts to the right and it becomes wider. That's interesting, and for the reasons you can read the paper. But basically, there's a lot of variation that happens because of programming, erasing, retention, and a lot of things. And as a result, the distribution, different cells get affected differently, and there's a huge variation between the cells. As a result, you get this widening of the distribution over time. And because you're doing programming over time, your voltages actually tend to increase over time. So that's what it looks like. And also, as you can see over here, now distributions start overlapping, right? So it's not nice. Okay, so that's one example. So basically, we concluded at that time that the threshold voltage distribution can be modeled with relatively good accuracy as a Gaussian distribution with additive white noise. Basically, you can model the distortion in the threshold voltage distribution over programming array cycles as an exponential function of the programming array cycles. This picture doesn't show it, but the paper actually shows that the way the mean and the standard deviation of the Gaussian distribution changes exponentially with the programming array cycles. Which means that at programming array cycle X, you can predict the mean and the standard deviation of the same distribution after some time. Like that programming array cycle 15K, for example. Now, if you know that, if you can do that, that's good. with more than 95% accuracy, now you can actually shift your threshold voltages. Right? You start with some threshold voltage at 1K cycle. You predict that it's going to be, okay, this much at 3K cycles. So when you're reading at 3K cycles, you use a different threshold voltage that you predict to be at that time. And while you're doing that, you actually calculate the real threshold voltage that you want to have. And then you use that. And basically, you can keep verifying your model online as well. So that's very interesting. And existing flash controllers do a lot of this, actually. And Gaussian distributions, not enough because it's only 95%. You want to be even more accurate if you want to minimize your orbit error rate. Because if you have a lot of bits, 95% is actually small. It's very similar to the branch prediction argument that we had, right? You may have, I don't know, 10 terabytes. And what is 95%? So you get actually, if your orbit error rate is even small, then you have a problem. Okay, if you want to read more, you can take a look at this paper. So later we actually realized that you really want this threshold voltage distribution prediction to be online and as little overhead as possible. And also, with smaller devices, this threshold voltage distribution becomes even harder to model. So this is a more recent paper that looks at essentially 1x nanometer devices, much smaller devices. And the distributions don't look as nice as you can see over here. This is, I don't know if you can see this very well. I don't know why my resolution is not very good. This is a very nice figure, actually. The projector is not doing justice to it. It's from this paper. But basically, if you look over here, these larger dots over here are actually the measured values. And the lines over here are Gaussian-based models. Those are the solid or dashed lines. Those are the Gaussian distribution, if you model them somehow. And you see that the Gaussian model is not terrible at 2.5 programming array cycles, but it's not very good also. So it cannot actually model this part. And there are weird effects, as you can see, right? There's this part over here. That's a P1 state, and it happens to overlap a lot with P2. So there are a lot of overlaps. And this is the scaling problem flash memory had, essentially. There are a lot of overlaps between the distributions. And that overlap increases, as you can see, at 5 kPe cycles. There's a huge overlap here between the blue and green, and also between the blue and red, the purple. And the overlap keeps increasing. As you can see over here, at 20K programming array cycles, there are a lot of errors. That blue state has essentially threshold voltages across the entire span of the threshold voltage range. And that's the scaling problem. Now the question is, how do you correct for these errors, right? So first of all, you want to model the distribution really well. And so this is better modeling, basically. We looked at a bunch of different distributions. It turns out the student's T distribution, T-based distribution, is a very good one. I'll give you the accuracy numbers in a little bit. And then based on that, this paper developed some mechanisms to reduce the error rates. But you can see that this actually models things really, really nicely. You can track the distribution nicely. That's good. And these are some example error rates that you see, basically. Gaussian is actually not terrible. But again, the numbers are not, because the distributions overlap so much, even an error rate of 2.6% is not very good. And of course, you need to do something else about these overlaps, in addition to predicting how the distribution will change. Okay, so basically, we looked at different models. Normal Laplace-based distributions are actually very good, but they're very hard to implement in the flash controller. A lot of calculations are needed. So it turns out students' T-based distribution is relatively easy to implement in the flash controller, such that you can actually predict what will happen next, and its error rate is not that far off from the normal Laplace base. So we're basically within 1%. We can model these distributions accurately within 1% today. But of course, this becomes harder as you go down below 1x nanometer. Okay, so this is, what is this? Okay, so this is basically the threshold voltage distribution as predicted by our dynamic model. So the curves over here, the solid and dashed lines, are predictions that are done based on what we observed until 10 kPe cycles. We predict what should be the distribution at 20 kPe cycles, because that's essentially what the flash controller needs to do. And the markers over here are actually the measured values at 20 kPe cycles. So this is the prediction versus reality. And you can see that it's not terrible. I mean, it's good actually, but there is a shift. So these dashed lines are prediction at 20 kPe cycles without knowing what happens at that time, only with the knowledge of these values. It's like this, and this is the reality. So the reality is a little bit worse than what we predict, as you can see. And that's exactly what the flash controllers do today. They predict the future and they try to figure out if the reality matches the future. Okay, so that's not too bad. And this is really the state of the artwork in planar flash memory that looks at how do you model these distributions accurately and the applications of that model. And I'm not talking about the applications of the model, but we're going to talk about some of them in a little bit. Okay. Okay, let's talk about other types of errors. We'll talk about program interference. When a cell is being programmed, the voltage level of a neighboring cell changes unintentionally due to parasitic capacitance coupling. And this can change the data value that's stored, of course. This is also called a program interference error. This causes neighboring cell voltage to increase, meaning to shift to the right. So you're increasing your own voltage, but you're also increasing the adjacent cell's voltage. This is like disturbance errors, but it's a program disturbance. So once retention errors are minimized, using refresh, for example, these errors actually become the dominant errors. If you remember that picture, that program interference was the second highest error cause after the retention errors. So how do we program current flash cells? We already talked about this. You basically use this two-step programming method. Okay, you program the LSB first and MSB next. So what is the program interference? Basically, it's going to be similar to what we've discussed with Rowhammer, except it's a very different error mechanism. You have a victim cell that gets affected by a lot of aggressors around it. And these aggressors are everywhere. Actually, all of these are aggressors, if you will. The good thing is, we want to look at how much each aggressor affects the cell. We're going to ignore this part because of the programming method that's used in flash memory. Usually, this gets programmed before this one. As a result, the programming of this word line doesn't affect the programming of this word line. Usually, programmers, the flash drive manufacturers program in an ordered way to minimize the effect of these interferences. So we're going to ignore these. We're going to try to model the change in the victim cell's voltage based on the programming of adjacent cells. So a traditional model actually that people have proposed and have been trying to use for some time was like this. Basically, this is the change in the victim cell's voltage level when adjacent cells are programmed. It's based on coupling capacitances and how much things are coupled to each other. You can see that if this changes by delta Vx, you have some coupling capacitance between this, and it's multiplied by 2 because it's a bigger, essentially it's a bigger effect than this one. But you can basically say that the delta V of the victim is a function of the delta V's of adjacent cells times the coupling capacitances of the adjacent cells. Now it turns out this is usually not accurate and requires knowledge of these coupling capacitors. So it's very hard to implement in general. So if you really know your chip very well, even then you may not know your coupling capacitances. So we wanted to actually have a more abstract model to do this. A new, more accurate and easier to implement model for program interference. And the idea is very simple. If you can empirically characterize and model the effect of the neighbor cell threshold voltage change on the threshold voltage of the victim cell, you can do better. Basically, you know the characterization, you know the results. Now you can fit the neighbor threshold voltage change using a linear regression model or any kind of model actually, but linear regression works well, and find the coefficients of the model via empirical measurement. That's the idea. So basically, this is the change in the victim's voltage, and these are it's really a sum of the changes in the neighboring voltages with some coefficients. And we want to learn these coefficients somehow based on the experimental data. And of course there is the voltage before the victim's old voltage. We should really fix the quality of this projector somehow because it's really bothering me. Okay, are you guys bothered with this? This is really low quality, isn't it? Okay. This was not like this before, was it? Okay, it was not. So we should really find a way of, I don't know what has changed here. Predictability is important. Okay, so basically we can measure the voltage of the victim before adjacent cells get programmed, and we can also measure delta V of the neighbors. So we can actually measure all of these delta V's here. The only thing that we don't know is the alpha values. And once we do a lot of measurements, we can fit this model to something, or we can also learn over time, right? Basically, that's the idea over here. So what we do is we do feature extraction for threshold voltage changes based on characterization. That's the threshold voltage changes on the aggressor cell and aggressor cells and the original state of the victim cell. And we have a linear regression model, and you can read the paper for more details. And basically, we use maximum likelihood estimation of the model coefficients to figure this out. And then you basically come up with coefficients, and then it becomes interesting. So the interesting part is this picture actually after you do all of that characterization. So this basically shows the relative importance of different aggressor cells, relative effect of the different aggressor cells on this particular victim cell. It turns out the immediately above cell has the most interference. Whenever that is programmed, its effect is the highest. 58% means that, assuming that the voltage of this is affected by 100% with everything, this contributes to 58%. And you can see that other cells are actually important also. These cells, immediately diagonal neighbor cells, are the second dominant cells. And even far away cells have effect. Actually, the word line that's after the immediate neighbor has an effect in flash. And there's no reason not to expect that. That's true for DRAM also. Actually, I believe Rohammer has a similar probability, except it's not easy to measure these voltages. The beauty in flash is you can measure these voltages to some precision. And also, basically, far neighbor cell interference exists, and actually victim cells, VTH, has negative effect on interference. So the higher your threshold voltage is, the less likely that you're affected by your neighbors. That's the interpretation of this. So I like this figure a lot because it's very interesting. I would love to do this for DRAM, for example, but it's not very easy to do. Okay, so basically based on this, you can develop a new model for program interference, and the model looks like this essentially. So we're actually going to eliminate these also, because whenever you're programming the neighboring bit lines as well. So these things actually don't affect you that much. They do affect you, but in incremental step pulse programming, because you're programming an entire page, you can take that into account and do the programming accordingly. That's why these cells that are next to you on the same word line are not that important. But this is important because once you actually program this, you cannot change this one unless you go back and reprogram that one, which causes a ripple effect because that also affects what's happening over here. So there's a problem, right? So these cells you can actually account for while you're programming the word line. But these cells are programmed after this victim cell, so you cannot do much about them other than understanding it. Okay, so this is the model basically, and we have the coefficients. And let's take a look at the accuracy of this. So what this picture is showing is, again, this is the chips, and this is the threshold voltage before interference that we have, and this is the threshold voltage after interference. If there was no interference, you should be on this line, x equals y line, right? Clearly there is interference. These are the measured results. So you can see that interference causes a shift to higher voltages. Okay. Well, I already said that, I think. This is measured before interference, this is measured after interference, and those are the red dots. And this is ideal if there is no interference. As expected, clearly there is interference in real systems. And interference causes systematic threshold voltage shift. But if you actually model it the way we did, you can actually adjust, you can actually predict. So basically the red parts, x and y, are now the threshold voltage measured before interference and the predicted with the model. And that's the model prediction. And this is ideal if prediction is 100% accurate. So it turns out our prediction is pretty good. Our model actually corrects for the threshold voltage shift because of program interference with about 97% accuracy, which is not bad. But of course, if you really want to be more accurate, you want to have an even more accurate model, right? Okay, there are many other results in this paper that discusses the program interference effects in MLC NAND flash memory, which I'm not going to go into. Okay, so what can you do with this model? I'll cover this and then we will be done. Basically, our goal is to mitigate the effects of program interference caused voltage shifts. So clearly, read reference voltage affects the raw bit error rate. As we discussed, you have a read reference voltage between two states. Ideally, you would like to minimize the bit error rate, and bit error rate is basically the area where these distributions overlap. That's what that says. If you select the read reference voltage to the crossing point, that's good. You minimize the bit error rate. If you select the read reference voltage to be like this, it's not good because that's not the minimum bit error rate that you can get. So there exists an optimal read reference voltage based on the distributions. And it's really predictable if the statistics, in other words, the mean and variance of these threshold voltage distributions are characterized and modeled accurately, of course. So the idea is to have optimum read reference voltage prediction. Basically, you start with some read reference voltage and distributions shift after some program interference or whatever effect that you have. And you want to predict that VTH shift such that you can adjust the read reference voltage to be this blue one as opposed to staying at the red one, which is not optimal anymore. So the idea is to learn this. This is called VTH shift or threshold voltage shift learning. This is done every some number of programming erase cycles, and flash controllers actually do this right now. You program some sample cells with known data pattern and test the threshold voltage. And you program some aggressor enable cells and test the victim threshold voltage after interference. And you characterize a mean shift in the threshold voltage. This is called program interference noise. I'm taking an example with program interference. Of course, there are many other effects that cause this threshold voltage shift. And to predict the read reference voltage, now your job is easy. Assuming you've done all of this, you have a good prediction for the shift in the threshold voltage. You take the default read reference voltage and add to it the predicted mean threshold voltage shift by the model. And this is true for different distributions. Different distributions shift differently, so you need to do it separately for ER, P1, P2, P3. Well, ER is usually not a problem, but everything over here, essentially. Hopefully that's clear, right? You basically predict how much you should shift the threshold voltage, read reference voltage, based on the threshold voltages you measure. And this is the effect that you get, basically. This is the number of programming erase cycles, and this is the raw bit error rate. If you don't do any read reference voltage prediction, your raw bit error rate is high. If you do read reference voltage prediction, your raw bit error rate after you adjust your read reference voltage is much lower. And that's consistent across basically all of the programming erase cycles. And let's do the study. Let's assume that you have a large BCH code. This is the acceptable bit error rate is 2 times 10 to the minus 3. This BCH code can tolerate that acceptable bit error rate, which means that you should not cross this point. You set your ECC. If you don't do read reference voltage prediction, you cross that point over here. If you do read reference voltage prediction, you cross that point over here. So basically, you improve your lifetime by 30% by doing read reference voltage prediction, which is really significant. And basically, you reduce the raw bit error rate by 64% also. And that paper also discusses these read reference voltage prediction. But the JSAC paper in 2016 that I mentioned also actually does read reference voltage prediction using much more accurate models. And that's the paper that I mentioned earlier. Okay, this is probably a good place to stop since we're out of time. But once you understand the distributions, you can actually do even more interesting things. And I'll start with neighbor-assisted error correction next time we have class. But that's not going to happen until after next week, because next week we have the exam on Thursday, and we'll have an exam review session on Wednesday, which means that you can come up with any questions, but it's good if you actually study the previous exams and lectures. That helps. So next week we're not going to continue. The really fun part will continue the week after. Sound good? Okay. Okay, see you next week then.